Alright, this is Precalculus lesson 21E. We're going to look at some word problems with exponents and logs. So it turns out quite a few things in the real world are modeled either with logarithmic functions or exponential functions. And there are certain times where we want to be able to solve those. So all the skills so far in this unit should kind of lead up to this. You should be able to read a problem, take a real world function that might be exponential or logarithmic, and both evaluate it and be able to solve it. So we're going to look at a couple examples and give you one to try. So this is straight from your book. It's talking about the risk of having a car accident based on your blood alcohol level. So it's a little hard to read this equation, so I'm going to rewrite it here. But it says that the risk as a percent is going to be equal to 6 times e to the 12.77x. And just stopping and thinking about this, we know it's some kind of an exponential function, which means that it kind of starts slowly but then rapidly increases. And it should make some sense to you that the more alcohol content you have in your blood, the more likely it is to have an accident, and that might actually get very large very quickly. So hopefully that makes a little bit of sense. So our question here is, how can I figure out how much blood alcohol would give me, according to this model, a 17% risk of a car accident? So in this case, it's actually asking us to find the x value given that r is 17. So I'm going to start off by writing 17 equals 6e to the 12.77. And this should look like a lot like a problem from last week where you were solving exponential functions where the x was part of the exponent. We learned that logging both sides of an equation is a good way to solve this. We also learned in that lesson that isolating the logarithm first is super important. So I'm going to start this problem by dividing both sides by 6 to isolate the e part of my formula. And then I'm going to take the log of both sides, and you have a choice of any logarithm you want from what we talked about in class, and hopefully from what you learned from the video. Natural logarithm is a great choice here because that's going to simplify the left side of the equation quite a bit. The natural log of e to the 12.77x is simply going to be 12.77x. So here's what I have. Natural log of 17.6 equals 12.77x. And when I solve for x and get x by itself, my final answer to this problem is going to be log of 17.6 over 12.77. Most of the time with a word problem, we'd like to have a kind of a meaningful numerical answer here. So x is going to be approximately equal to 0.08. So that means that if you have that level of blood in your system, alcohol in your blood system, then your chances of having an accident are 17%. Interestingly enough, this number right here is actually the legal limit for a lot of states, including California. So that means if you drink alcohol to the limit that becomes illegal, you're actually already at a chance of 17%. Higher than that, your chances of having an accident go way, way, way up. Good thing to keep in mind. Alright, our second example here is a population problem. A lot of populations, as we talked about in class, have exponential growth used to model, and it's a little hard to read this one too, so it's e to the 0.0126t, and this models the population in California. So 2 questions to answer here. First one is, what is the population in 2005? Well, since the model, as we see from the problem up here, t is measured since 2005, so the year 2005 is actually in our formula year 0, right? So I'm actually finding what is the population of California in the year 0, and so that gives me 0 in this exponent. E to the 0 is 1, and so 36.1 million is my answer. And it's in millions of people, so according to this model, that was the population in 2005. Okay, second half of this question is when will the population, according to this model, reach 40? So now 40 is kind of the answer to this question, and I want to solve for t. Right? So I've got to take the 36.1 e to the 0.0126 t and solve. And this right away looks a lot like our last problem where I have a variable that's in an exponent and I have to solve. I'm going to use logarithms again, but remember isolating first is important. So 40 over 36.1 would be equal to e to the 0.0126 t. Natural log of both sides, like our last problem, is convenient because it will cancel that e on the right hand side. And I'm going to go ahead and take advantage of that and just write this as 0.0126 t. And I'm very close to my answer because t is going to be that logarithm, log of 40, ln of 40 over 36.1 divided by that number 0.0126. And again, a meaningful answer is helpful here. I think that turns out to be 8.1, about. Okay, and since the question is what year is that happening, I want to make sure I interpret that. So remember that my base year is 2005, and so the number here I found is the years since 2005. So the actual final answer to this one should be 2013 is when this population would have, when California would have a population of 40 million. Alright, here's a U-try. We're going to look at the population of Texas. It's going to be very similar to the last problem. If you understood that one, you should have no problem with this one. In case you have a little trouble reading that, it's A of t equals 22.9, and then it's e to the 0.0183. 0.0183 t. Okay, see if you can answer the first question. Alright, since our model is based on the years since 2005, the population in 2005 would be just A of 0. So plug in 0 and you get 22.9 million. Okay, look at question B, try to interpret that and give us an answer. Be sure to answer the question precisely there. Alright, our solution here involves plugging 27 in for the population and solving for t. Once again, I've got to isolate my exponent, that's this line, natural log both sides, that's this line, and then solve for t, which is this line. I get an answer of 9, but the question is when will the population be at that level, and it's 9 years since 2005, so your final answer should have been 2014.